Okay, I wanted to finish up what we started in lecture, which is the longest increasing subsequence problem, which is the proto-dynamic programming problem. So it's important you understand this if you want to understand dynamic programming. Okay, so let's go back to the LIS problem, and let's remember that the longest increasing subsequence is simply the subsequence of a particular sequence that is increasing. And of all the subsequences that are increasing, the longest increasing subsequence is the longest one. So in this case, the longest increasing subsequence of 6352781 is 3578 because that is a 4-element increasing subsequence. So now the question is, the problem, I should say, is what how do we determine the longest increasing subsequence? So we had a couple approaches that we discussed last time. The first approach was simply the naive approach, where you have a sequence and you know for every element in the sequence, it could either be part of a subsequence or it could not be part of a subsequence. So you basically enumerate all the possible subsequences of a particular sequence. So in the case of 63527, you enumerate all the possible subsequences. You have 637, you have the subsequence 5, you have the subsequence 6527, and you enumerate all these possible subsequences, and you then check to see which of these subsequences are increasing. For instance, all the single element subsequences are increasing, of course. And from those increasing subsequences, you simply store the longest increasing subsequence. So this case is inefficient, right? It's inefficient because you're spending computing power on subsequences that are never going to actually increase. So for instance, right here, when the suffix of the subsequence 5 is 5-2, you know that whatever you add or don't add to the prefix of the subsequence isn't going to result in a increasing subsequence. So all this effort here is just wasted, right? So the naive approach basically looks at all the possible subsequences, it enumerates over all the possible subsequences, and then checks each subsequence to see if it's increasing. And if it is increasing, then it records the maximum increasing subsequence. So this approach takes n to the 2n time. It takes 2n subsequent. It takes 2n because there are 2 to the n subsequences. And it takes n time because you want to check each subsequence to see if it is increasing. So this is an ideal, right? This is a very, very large asymptotic bound. And as mentioned before, it's large because we're wasting a lot of cycles on calculating non-increasing subsequences. So the first optimization we do is to add in a check to see if a subsequence, if going down the rabbit hole and adding an element to a subsequence will result in an increasing subsequence or not. If right at this point, if we know adding 5 to the subsequence will result in a non-increasing subsequence or even not LIS, then we shouldn't ever add 5 to the subsequence. We shouldn't even consider this case. So the first optimization is to prune these parts of the branches. We go to this part, we reach this node, and we say, okay, there's 2 already in our subsequence. Can I add 5 to the subsequence and still have a longest increasing subsequence? No. Well, then I don't consider this part. And then I only go down this tree. Again, same thing here. Can I add 3 to this subsequence and still have an increasing subsequence? No. So why do I need to calculate these subsequences anyway? So that's the first improvement we do, and that is what we know as backtracking, right? Our backtracking approach has a logic where we have a prefix of the sequence, and we have the smallest element in the subsequence. And we say that if this element, that we can only add an element to the subsequence if it is smaller than the smallest element in the subsequence suffix currently, right? So if we look at the recursive tree, in this case, we consider the case, for instance, if we add 1 to the subsequence, then our x becomes 1, which is the smallest element in the subsequence. And every time we try to add another element from the sequence prefix to the subsequence, we say, okay, is this element less than 1? If it is, we could add it. But if it's not, then we can't add it, right? And we only consider the case where we don't add that element. So since 1 is the smallest element in the array, then once we add 1 to the subsequence, there are no more elements we could add and still get an increasing subsequence. So we don't even consider those cases. The result of this pruning is that we reach the end of this tree, and every one of these leaves is a increasing subsequence. So we have 5, 7, 8, we have 2, 7, 8, we have 1, we have 6, 7, 8, and in fact we have the longest increasing subsequence, which is 3, 7, 8. Right? So that's the beauty of backtracking. You save a lot of cycles. Now, the fault of backtracking is that you don't necessarily get a nice asymptotic bound. For instance, here, if you have the sequence 1, 2, 3, 4, 5, and you use a backtracking algorithm, you're still going to enumerate over all the possible subsequences available, right? Because every subsequence of this array is an increasing subsequence. So you're still going to have a complexity of O to the 2n. But because you are doing that increasing check at every step of the call, of the recursive call, you get rid of that n term that you had with the naive approach. However, just getting rid of one n term isn't good enough. We have to get rid of this 2 to the n, right? And what we notice is that we have a lot of trees which seem very familiar. So for instance, we have a function call here where we have an array 635 and the smallest element in the subsequence is 2. We have this function call here. The array is 635 and the smallest element is 2. Now the subsequence that we've added are all the same, are different. Each of these subsequences are different. But the function call is the same. So that's an interesting thought, is because you're effectively calculating LIS 6, 3, 5, 2 4 times. You're calculating it here. You're calculating it here. You're calculating it here. and you're calculating it here. The subsequences that you already added are just like a variable at the top level. But the function call is still these two inputs. And so you come to realize that your input space is constrained, right? There are only so many inputs that you could feed into the LIS function. And there's way less than 2 to the n inputs. In fact, if we look at the LIS function here, we know two things: that this prefix, how many prefixes of the array are there? Well, there are n prefixes. And there are how many possible values of x are there? Well, x has to be a particular element of the array, right? So you have n possible values, elements of the array. So you're in this situation where you have n by n possible inputs to this array, to this function. You have n prefix arrays, and you have n possible values, n elements of the array. And so this seems like something we can optimize. This seems like something that we should remember so that we don't get into the situation where we're calculating the longest increasing subsequence of the prefix 635 given a constraint of 2 4 times. We should be only consider calculating it once. So how do we memorize the recursion? That's the question. If we memorize it well, we will end up with something along the lines of an n squared running time, because each call takes O to 1 to assemble the answer. So we have n squared problems, so n squared space and n squared running time. Now the question is, how do we structure it? How do we structure the table of previously computed functions, and how do we call them, do the comparison? And for this, it requires us to know the problem very well. And so how do we really dissect the problem? Well, we know that we have experience with recursive definitions before, so maybe we could define this problem in terms of a recursive definition with a base case and an inductive step. Sorry, I mean recursive relation. And so that's what we do here. We know that at the base case, if there is no prefix, then regardless of what the constraint for is, the smallest value in the currently established subsequence, regardless of what this value is, then the LIS for no elements is 0, right? Because we don't, if the prefix array has no elements, then we can't add any more elements to the subsequence. However, now we want to know, what if the prefix, it doesn't have 0 elements? What if it has 1 element, or 2, or 3, or 4, or 5? Well, the question is the last element of the prefix, the ith value, AI value. Is this value larger than the smallest value in the subsequence? So if if it is larger than the smallest value in the subsequence, we can't add AI to the subsequence, right? Because, let's go back to our old friend 635. Let's say that's prefix. and our constraint is 2, let's say the subsequence is equal to 2, 7, then adding 5 to this subsequence would negate the increasing property, right? So we can't just add 5. So we can never add 5 because 5 is greater than the smallest element in the subsequence. So this smallest element in the subsequence is some value it contained in A. And we say if it is larger, then we simply consider the case where we don't add this value. Then we recursively call LIS, assuming we don't add 5, 6, 3, and constraint 2, and so on, right? The second option is that maybe the constraint is large. Maybe the subsequence value is equal to 7. That's the subsequence so far. And we call LIS 3, 5, 3, 5, 7, 3, 5, 7, 2. Let's say. So the constraint in this case, the smallest element in the subsequence would be 7. And so we can add 2 to the subsequence, right? But if we add 2 to the subsequence, then that would stop us from adding 3, then 5 to the subsequence as well. That's an issue. So we have two options. The first option is that we don't add the element AI to the SS. The other option is we do add it. Add AI to SS. If we add this particular value to the subsequence, then we call LIS on the rest of the prefix, and we change the subsequence constraint to the new smallest value in the subsequence, or at least the index of the new smallest value in the subsequence. Okay? So that's what we're doing. We have a base case where if there is no prefix, then you can't add any more elements to the subsequence. And we have a recursive relation where either our smallest element of the subsequence is smaller than the last element of the array prefix, which means we can't add the last element of the array prefix to the subsequence, or the last element of the array prefix is less than the smallest element of the subsequence, which means you can either ignore this element, hoping that more smaller elements come along earlier in the prefix, or you do add the element to the prefix. Okay, pretty simple. So we have this recursive relation down, and the question is, now we have to organize the calls, right? We have to organize them in a manner so that we can calculate the LIS, the top level call, which is LIS A infinity, right? So the first thing we'll do is, in addition to this value x being one of the elements in A, we'll also add infinity, right? Because when there's nothing in the subsequence, then the smallest value in the subsequence is infinite. and you're always able to add another element to the subsequence. Okay, so that's the first thing we'll do. We'll add this array infinity, and this infinite array is simply to mimic the top level call, the final value that the LIS function could be outside of the array values. The next thing we'll do is we'll arrange the prefixes, all the possible prefixes of the array, and all the possible elements of the array. So notice we're indexing the array from index starting at 1. And so we have to arrange this in a manner that we can calculate from the base case up until the complete size of the array. And it helps if you actually look at the recursion tree when you do this. And when you look at the recursion tree, you see that you have this base case at the leaf, and then you slowly work your way up towards the array prefixes to get to the top level value, right? So it makes sense that we arrange the array prefixes from a prefix of 0 to the prefix of complete. And we'll, of course, arrange the values of x from the x being the first element of the array to x being the last element of the array. Okay? So, how do we fill in this table? Well, we know that these calls here, for instance, LIS 6, 6, never happens. Never happens. So why is that? Because LIS 6, 6, x can only be 6 if you add 6 to the subsequence, right? But here, you haven't even added 6 yet to the subsequence. You haven't added this element to the subsequence yet. So it's impossible for x to be 6. So this value cannot happen. And subsequently, none of these values can happen because you haven't added 6 to the subsequence yet. Similarly, LIS 6, 3, 3 never happens for the same reason. Okay? So right off the bat, we have an area of the table which we don't need to fill out. So the next thing we do is we try to fill out the base case. And the base case is simple. If the prefix is not, then there are no elements that can be added to the subsequence, right? So this is all 0. Regardless of what the x constraint is, the smallest element in the subsequence is, none of these, there are no more elements to add to the subsequence. Okay, so that takes care of our base case. Now, we need to start filling in the table row by row. And for instance, right here, let's take this element here. Let's use a different color. This element right here, I equal to 1, j equal to 2. We say that, okay, AI, A1 is equal to 6, AJ is equal to 3, right? So this right here, we know that the constraint is smaller than the last element of the array prefix. And so we can't add 6 to the subsequence with this constraint. So we fall into this category here. And so we know that LIS is equal to I minus 1, j it's equal to this value here. And we simply put 0 here, transfer. Okay, now let's consider a different case where sorry, that should be no. That should be ignored. Let's consider a different case where A1, where we have an element, let's say I is equal to 1, and A and J is equal to 5. Okay, so AI, the smallest element, the last element in the prefix is equal to 6, and A of 5, the smallest element in the subsequence is 7. Okay, so in this case, we have a choice. We have a choice here. We have 6 is less than or equal to 7, which is correct. And so, either LIS we look at LIS 1, negative 1. Either we consider a case where we don't add this element to the array, 0, or we consider a case where we do add this element to the array. And we take the max of that. Okay? So we take the maximum of these two options, and since both these options are 0, then the maximum will go to the second one, which has this plus 1, and so we put 1 here. Okay? And we do that for basically every single row. We look at the rows, we look at the possibilities, and we say, okay, we consider what part of the definition we're in, and we follow the recursive structure as we laid it out. So again, don't focus too much on unrolling the recursion. It's one of those problems like Tower of Hanoi, right? If you try to keep unrolling it and keep defining the output for various inputs, you're going to go nuts. All you have to do is define the recurrence relation and define the base case and order the computation of the input space correctly so that you fill out the table. Okay. So you go through this, of course, and fill out the table. And finally, what you're left with is this last element which says that for the function call LIS of 6, 3, 5, 2, 7, 8, 1, given a subsequent constraint of infinity, because there's no elements added to your subsequence yet, the longest increasing subsequence is of size 4. Okay? So hopefully that makes sense. You just fill out the table row by row, and eventually you'll get to a point where you get this final number. Okay, so this is literally the algorithm that we just did. It's 2 nested for loops, of course. One, you're iterating over the rows, and the other, you're iterating over the columns. This is all the possible constraints of the subsequence. This is all the possible array prefixes. And so the running time and the space of this would both be n squared. So one of the things to consider is that it's very easy to do this problem in linear space. And how would you do it in linear space? Well, looking back at the table, every one of these computations looks at either its own space position or another space position. Oops, not 3. So it's either at every row, you're either looking at the previous value of the cell or a value earlier in the array. So you could squash this array out, down into a single row, right? And compute it that way. So you can compute this in a linear space. And in fact, most of the solutions you see on YouTube or Google have this linear space. But we go through the table version, the n squared version, just to hopefully make things clear. So we know the actual size of the longest increasing subsequence. So what is its value? The value, the actual increasing subsequence, how do you find it? Well, it's pretty simple. For each of these times, let's take this value here. This value, this computation here. This computation, when we did it, we looked at AI, which was equal to A7, which is equal to 1, which was equal to 1. And we look at AJ, which we labeled A8, which is equal to infinity. Okay? So, we saw that AJ is definitely larger than AI. And we could either add the element, or we could either add the element or not add the element, right? Now, if we don't add the element, we traverse vertically. If we do add the element, we traverse diagonally through the table. So that's how we tell if we added the element or not to the subsequence. If we look at the actual dependencies, the times where we traversed, we see that, okay, when the last element was 8, we went diagonally. Then when the last element was 7, we went diagonally. Then when the last element was 2, we didn't go diagonally. So 2 isn't part of the subsequence. Then when the last element was 5, we went diagonally. And when the last element was 3, we went diagonally. And when the last element was 6, we didn't go diagonally. We didn't add that to our subsequence. And so our longest increasing subsequence is 3, 5, 7, 8, just by analyzing when the table elements took this value. Okay? And you could add a little snippet to the code to record when you take this value. And as long as you record this pointer, then you could work your way back from this element here and find all the elements that are part of the longest increasing subsequence. So, one thing to note is that there are faster algorithms for longest increasing subsequence. They use a different type of recursion and a different optimization technique, and it's too complicated to explain, especially for an introductory course. But I think Geeks for Geeks has a good explanation of it if you want to take a look. Okay, so let's summarize what we've learned about dynamic programming. So, dynamic programming is a type of smart recursion for which the number of distinct subproblems is small, i.e. polynomial time. And so to do a dynamic programming, to find a dynamic programming solution, you should estimate the number of subproblems and the time to evaluate each subproblems and the space needed to store the value. And then that will give you an upper bound of the total running time if you use automatic/explicit memorization. And then you come up with the explicit memorization algorithm for the problem and eliminate the recursion and find the iterative algorithm that just uses for loops, right? And so the big challenge is finding the right way to order the subproblems, uh, and their evaluation. That's the whole point of a dynamic programming algorithm. And lastly, of course, there are methods to optimize the results further. So just like we saw with the LIS problem, you start off with a table that has n squared solutions, but you could optimize it to n size table. So once you have a dynamic algorithm, programming algorithm going, it's very easy to further improve it. And so that will be what you are going to be doing in your lab tomorrow. So keep this problem in mind, and hopefully your TAs will help you practice dynamic programming this week and next week. All right? Have a good night, guys. Good night.